Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a concept of momentum equation. In this momentum equation, we'll derive the equation when the fluid is flowing through a pipe and when the pipe is in bending condition. So before going to derive this pipe bend condition, let's try to understand what is this momentum equation and how we can derive that equation from normal fluid. So actually this momentum equation it is the law of conservation of momentum, or we can say this is based on the momentum principle. Okay, either we can say it is based on the principle of law of conservation of momentum, or we can say it is based on the momentum principle. And that momentum principle or the law of conservation of momentum, it says that the net force which is acting on a fluid mass, the net force which is acting on a net fluid mass, okay, is equal to the change in momentum per unit time. Is equal to the change in momentum per unit time. So here what are things? Net force is there, fluid mass is there, and time is there. These are the three things out there. Okay. As for the definition, we can derive that equation, but the equation will be taken from the Newton's second law of motion. Okay, the Newton's second law of motion, we know that the force equal to, we can write mass into acceleration. Okay, so we know that acceleration equal to, we can write the change in velocity with respect to change in time. Okay, and just put this value of acceleration in this equation. What will get? The mass into change in velocity with respect to change in time. Again, the same equation I can write. This mass is a constant term. So what I'll do it, I'll take this mass term inside this derivative part. So that one we can write derivative of mass into velocity with respect to time. So this is F equal to this one. So this is the net force equal to, as I told, the net force equal to the rate of change of, or you can say the change of momentum with respect to time. So this is the change of momentum, because we know that momentum equal to, if I write again one more term, momentum, we can write, we know that momentum equal to mass into velocity. Okay, this is the normal equation for momentum. If you want to write the momentum per unit time, okay, if you want to write the momentum per unit time, so here also we can write the same thing, mass per time into the velocity. Now this mass per time, what we can write here, we can write rho into V, because we know that, again one more term we can write here, rho equal to mass by volume. So we can write mass equal to rho into volume. So the same thing I can keep it here, volume by time into velocity. Okay, this is volume and this is velocity. Now volume per time, you can say, okay, this is volume per time, or we can say the volumetric fluid per rate. Okay, so this one we can write the discharge or the rate of flow, we can write here. So that one we know that we can write rho into Q into V. So this is our momentum per unit time. This is another part is there. We'll discuss this one also. Okay, up to here you understand force equal to derivative of mass into velocity. So this one we can give an equation 1. And this equation actually, this is known as the momentum principle. Okay, and from here also we can write one more thing. We can write this term into F into dt equal to derivative of mass into velocity. So this also we can write, and we can give the equation 2. And this is actually known as impulse momentum equation. Okay, This is known as impulse momentum equation. And which, if you see this equation, impulse momentum equation, what I'm telling, see, this is our momentum principle. Okay, and this is impulse momentum equation. Now this is stated that the force F, which is acting on a fluid mass, okay, and with respect to the interval of time, this is dt, okay, is equal to the change in momentum. Change in momentum is nothing but mass into this derivative of mass into volume. This is our change in momentum. So which direction the force is applied? In the same direction that need to be considered. Okay, so I hope you understand up to this. Now this principle, okay, we are going to apply on a pipe bend condition. So now we are going to derive the force exerted by a flowing fluid, in a pipe bend. When in a pipe bend, when there is a fluid is flowing through a pipe, and especially it is considered the bending pipe. Okay, normal pipe not there. Normal pipe means we know that there will be a flow in a either horizontal pipe, okay, or we can say there is a flow in the vertical pipe will be there, suppose. Okay, and but here we have taken a bending pipe. The pipe is in bending condition. So when the fluid will be flows through this bending pipe, so what is the force is going to be exerted by the fluid on the pipe? So that we are going to calculate from here. And for that, here we have taken two different sections up there. This is section 1 and this is section 2. Okay, this is section 1 and this is section 2. At these two sections, we can say, okay, that there is a pressure of fluid is there is a velocity of fluid is there, and the area of cross section of the fluid which is flowing through the pipe. So these are the terms are there in section 1. What are terms? Now pressure 1 PA, P1, and velocity at section 1 B1, and similarly area of the cross section A1 at the section 1. Now similarly we can say for the section 2, that is nothing but we can write the pressure P2 and the velocity V2 and the area of the cross section A2. Okay, so these are the parameters, or you can say the characteristics of the fluid which is going to consider for this pipe flow. Okay, now these are the two things are there. Now you can see when the fluid is flowing in this pipe, now how the fluid movement is there, that we need to consider here. Right? It is moving in this directions. Okay, now here again we need to consider two different forces. One is force in the x direction, another one is the force in the y direction. Okay, because we need to find out the total net force, or we can say the summation of force is how much. So before that, let's find out what is the force in the x direction and the force in the y direction. So for that we will do one thing. Let's consider Fx and Fy are the component of the force exerted by the flowing fluid, or the force which is exerted by the flowing fluid, and in the bending pipe, in the pipe bend on x direction and as well as y direction. Okay, so these are the two forces what I have written here. These are the two forces are the force exerted by the water on this pipe bend, in the x direction as well as in the y direction respectively, you can say. Now the force exerted by the bend on the fluid in the direction of x and y, as I told you, this will be, x and y should be equal and opposite. Okay, this should be equal to fx and fy, but these two forces, what we have considered actually, it should be equal. It should be equal, but it is in opposite in direction. It is in opposite in direction. Okay. So we can see these two components, what are the force components are there. We can say, so let me write the force Fx, I can say the component of force exerted by the bend of the pipe on the x direction. Okay, so this is Fx equal to, here we can consider that is minus Fx. Now you can ask why it is considered the minus Fx. I'll tell you that one. Now see, the force of this fluid, or the impact of this fluid on this pipe bend, this is moving in the x direction. But after striking on the pipe, okay, this force will be give a reverse impact on the fluid. So the force exerted by the bend on the fluid. See, now this fluid is giving impact on the bend pipe. Now again, due to this bending in pipe, the fluid also is getting a reverse force on the fluid due to this pipe bend. So we need to consider that is minus Fx. Okay, and similarly in the direction of y, if you consider, so that will be minus Fy. Okay, these two are the things. And the other external forces which is acting on this fluid, okay, the other external forces is nothing but it is a pressure force. Okay, and that at this section 1 if you consider, or at the section 2 if you consider here, so that is, we know that the pressure force P equal to force by area, and similarly we can write the force which is acting on this point F equal to, we can write P1 A1, okay, which is moving in the direction of x. And similarly at the section 2 if you see, so that is P2 A2, P2 A2, but it will be in the opposite direction of the fluid flow. Okay, that will be give you a impact on this second section, so which is opposite in direction. So this is P2 A2 and this is P1 A1. Okay, now we need to find out, now we will write these things. Okay, the momentum, let's write the momentum equal to, in the x direction, the momentum in the x direction. So what we can write a momentum in the x direction, as I told you previously, momentum equation, we can write mass into velocity, and from there we can write this. Okay, so the momentum equation we can write in the x direction, so mass into velocity. Okay, now the net force which is acting in the direction of x, you can write the net force which is acting, or you can say the summation of force which is acting in the direction of x equal to the rate of change of momentum. The rate of change of momentum in x direction. Okay, see this equation, because this is the starting one and it's very easy. Summation of x equal to rate of change of momentum in x direction. So summation of x is nothing but the total how many forces are acting on the fluid by the fluid on the pipe and in say x direction only. Only we need to consider the x direction here. So let me go to the next slide. So before going to the next one, so let me see here. See, now at this point if you see, let me draw here the force which is acting here at this point. At this point there is force is only x direction force, that is Fx. Okay, and there is a pressure force which is acting here. But similarly if you see in this section 2, at the section 2, okay, the velocity which is coming out, or the pressure force which is acting here. Now see this. This is the section 2. Now at this point, this is the movement of P1 and pressure force P1 and A1. But at this region, if you see, where the pressure force which is acting at this section 2 in this point, like P2, A2. Yeah, the diagram already drawn here. So here if you see at this point, P2, A2 is there, and P2, A2 makes an angle of theta to this section. This is makes an angle of theta here, because it is in bending in pipe condition is there, it is not in a horizontal condition. Okay, now this pressure force need to be considered in the, or it need to be resolved in the x direction as well as y direction. Okay, so this one, if you resolve in the x direction and y direction, is done already here. So that will be considered P2, A2 cos theta, and in the vertical direction P2, A2 sin theta. Okay, why I'm telling this one? Because here the pressure force what we have considered in this at this point in the x direction. Similarly, at this point we need to consider in the x direction. Okay, but here if you see, it is in the reverse direction. So let me write. So I can write one thing: the F1 plus F2 plus the force in the x direction equal to the rate of change of momentum in the x direction. So rate of change of momentum, that is already I told, the mass into velocity with respect to time. I'll directly add this value, that value here. So here F1 equal to, as we have seen, we can write P1 A1. P1 A1. We can see here, this is the P1 A1, the pressure force at the section 1. Okay. Similarly, F2. If you see the F2, that means here. Okay, the pressure force which is acting at this point. So it is acting here, but it is acting with inclination. So that one we cannot consider. So what we need to do, because we are considering only x direction, in this direction. So this is makes an angle of theta. So if you will already resolved here, so the what will write, so the F2 we can write, that is in the negative direction. If you see, it is impacting on the negative direction is there. So that may reverse direction if you say. So that value will be minus. So we can write P2 A2, that is cos theta, and the force which is acting in the x direction on the pipe bend, so that will be minus Fx. As I told you previously, that will be minus Fx. And the rate of change of momentum is nothing but, already I told you here, the rate of change of momentum is nothing but rho qv. So that is nothing but, already found this one, the mass by time into velocity. Mass equal to, we can write rho into v into density in volume into velocity. So volume by time, that the volumetric flow, and that can be written rho qv. Okay, so this one we can write rho q and into v. So that is v is nothing but, we can write the initial velocity, or the, you can say, final velocity minus initial velocity. So final velocity is nothing but, you can write v2 in the x direction. So v2x you can write, and here you can write v1x. The final velocity in the direction of x, and initial velocity in the direction of x. So v2x minus v1x you can write, or you can write only v2 minus v1. Anything you can write here. Now these things what I'll write here, this one I can just write rho q. So again we need to find out this value here. Okay, now this one I can write P1 A1 minus P2 A2 cos theta. This is the total force, and this is minus Fx equal to rho into q into v2x minus v2x. So what is the final velocity and what is the initial velocity? Initial velocity is as usual, only v1 is there, and what is the final velocity, that need to be considered here. Now if you see again, initial, as I told you, v1 is the starting velocity which is moving in the direction of x. There is no problem, only v1. But the v2, if you see, when it is moving out at the section 2, now it is also acting with an inclination here. Okay, it is acting inclination here. Now this movement, if you see, v2, if you want to resolve in both direction, x direction and y direction, because I need to consider the velocity in the x direction. So again, the same velocity we can resolve with an angle of theta in the x direction and y direction, that is v2 cos theta and v2 sin theta. Here, if you see the direction, how this fluid is coming out. So this fluid is coming out here. So similarly, the direction will be in this x direction and it is y direction. There will be no negative term will be here. Okay, but in the pressure force case, it is different. Okay, it was acting in this opposite direction. Okay, so this is here. Final velocity is in the x direction, v2 cos theta. Now, what I'll do here, I'll write just v2 cos theta. And this one, we can just write in, see, we need to find out the force in the x direction, as I told you, and we need to find out the force in the y direction. So what I'll do, I'll just keep fx in one side, remaining terms I'll take it to other side. So what will be the final one? Fx equal to rho q. Here I will just minus term I have taken here common and I have just multiplied here. So you can write v1 minus v2 cos theta plus p1 a1, and this is minus p2 a2 cos theta. This one we can give some equation. Any equation I have given? Yeah, equation 2 up to we have done. Next, this one, equation 3, we can mark it here. Okay. Yeah. Now this is in the force in the x direction. Similarly, we need to find out the force in the y direction. The force in the y direction we need to find out. Okay. So these things also we can write what? Now what is the force? Okay. Let's go to the diagram again. Now here, if you see, this is moving in the x direction. What about the pressure force which is acting y direction? So there is no pressure force is acting on the y direction. So what value we have written here? F1. Now here, if so, we can write F1 plus F2 plus Fy I need to consider. And similarly, we can write again the same mass rate of change of momentum, that is mass per time or mass per second into velocity. Now this is the force, this is the pressure force which is acting at the section 1, but we need to consider in the y direction. If you see the y direction of pressure force is here, there is nothing, pressure force is acting in the y direction. So this term will be 0. And what about this pressure force 2 at the section 2? If you go to the pressure force section at section 2, so that is here. That is nothing but P2 A2 sin theta. So this is also in the reverse direction, you can see. The impact in the reverse direction is showing. So that is minus P2 A2 sin theta. And this is also, again, if you go to the diagram, now see, the fluid is moving here, but the force which is acting here at this, in this direction, but after hitting here at this pi bend, again is going to be reverse in this direction. So that will be also minus Fy equal to, here also again we can write rho q, this one we know that value, rho v q, correct, or rho q v. So here you can write rho q into the velocity. What is the final velocity? That is, you can write v2y minus v1y. Anything I can write here, only v2 I can write, but though I am considering the y direction, so let me write in the y terms. So again, I'll just expand this term. So that is nothing but P2 A2 sin theta, and this is minus Fy equal to, I can write rho q. Yeah, let's write rho Q, and this is V2y. Let's go to the here. Now the velocity in the y direction. The velocity in the y direction, that is nothing but V2 sine theta. Now this V2 sine theta, and what is the initial velocity here? Initial velocity also we need to consider in the y direction, that is also 0. Okay, so I can write this is V2 sine theta minus 0. This velocity in the at this first initial condition at this point, because we are considering only y direction. Okay, so the value of this velocity will be in the y direction is 0. Now again, I'll just write this one. We'll keep the Fy only one side, and remaining term I'll take it to other side. So I can write here rho Q, and this minus V2 sine theta, because see, this side minus is there, so I'm taking suppose minus common from here, and I'll multiply the minus negative term here, so we'll get rho Q minus of V2 sine theta, and this is plus, only 0 is there, nothing required. Now this term we can take it to this side, so already plus is there, so that will become this side, now it will be minus. So P2 A2 sine theta. So this is our equation 4, and this is the force in the y direction. This is the force in the y direction. I hope you understand. This is the force in the x direction. Okay, now we need to find out the resultant force. As per our definition, we can find out the net force or the resultant force equal to root over of what is the value we got, the force in the x direction plus the force in the y direction. Okay, this is the resultant force, and similarly we can write the angle made by the resultant force with the x direction or with the horizontal direction. So that one we can write tan theta equal to Fy by Fx. So this is one equation, tan theta equal to this one, and this is our resultant equation. Okay, these are the two equations up there. Now I hope you understand this derivations of this force exerted by the flowing fluid on a pipe bend. The concept is very simple and clear. We need to just find out what are the forces are acting at these two different sections. We have taken this, this is one section and this is one section, and just we have found and we have just identified what are the forces are acting, like what are the forces, net force acting at this point and the section 2. So only one formula we have started. See, if you see the net force F equal to ma, here Newton's law of second law we have started. Okay, then we just taken this impulse momentum equation, and from there only we have started. Okay, now the summation of force equal to the rate of change of momentum as per the momentum principle. We just derived this one. So we need to find out the summation of force equal to, this is x direction, similarly summation of force in the y direction also need to be considered. So we just need to see this is only the starting formula. After that we need to see that at section 1 what are the forces are acting, and at section 2 what is the force acting, and what is section 1 what is the velocity acting, and section 2 what is the velocity acting, so that we can find initial velocity and final velocity, that to be in the x direction as well as in the y direction. Okay, now if you see, remaining things are as simple as that, and just we have taken, see, this is a force in the starting force, and this is a pressure starting pressure second section force which is there in the inclined direction. Just we have resolved this force in the two components, x component and y component. So here two things we have resolved, one force, another one is velocity. Okay, this is a force, or you can say here section 2 the reverse force which is acting here, opposing force. This one we have resolved, this one, and the velocity we have resolved in the direction of force, in the direction of fluid. So I hope you understand this equation. If you are having any kind of doubt or query regarding this, you can give a comment on the comment box. Thank you all.